Hey everyone, and welcome to This Explainer. I am so thrilled you're here today because, well, we're going on a seriously fascinating journey. We're going to zoom way down into the invisible rules that completely govern our physical world, and then zoom all the way back out to see how those tiny, microscopic rules create the massive everyday reality we all experience. I mean, from the water you drink to the very air you're breathing right now, matter is secretly following this incredibly strict set of hidden instructions. Let's get into it. Okay, let's dive into this and start with a question you probably haven't really thought about since you last dropped an ice cube into a glass. Why does that ice float? I mean, why is solid water actually lighter or less dense than liquid water? Almost every other substance in the entire universe gets heavier and denser when it freezes into a solid. But water? Water is this bizarre rebel. To understand exactly why it breaks the rules, we literally have to uncover the secrets matter hides at the microscopic level. So, here is our roadmap for today's explainer. We'll briefly cover the 3 states of matter, then look at the invisible forces between us, the laws governing gases, the ideal gas equation, and finally, mixtures and movement. Don't worry, we're starting simple at the microscopic level and building our way up to the bigger picture. All right, section 1, the 3 states of matter. Let's zoom out for a second. Just take a quick look around you right now. You're interacting with the 3 fundamental states of matter we experience daily, right? Your chair, your coffee, the air in your room. And beneath the surface of those states, something absolutely brilliant is happening. And this brilliantly illustrates what I mean. Notice how in a solid state, like your chair, the particles are packed tightly together in this highly regular, highly ordered pattern. They are firmly locked in place by strong forces. Now contrast that with the gas state. It's totally chaotic. The particles are practically socially distanced. They're moving randomly, existing super far apart from one another, with pretty much negligible forces holding them back. Because of those particle distances, we get some very specific macroscopic properties. Solids have a definite shape and a really high density simply because their particles are tightly locked. You literally can't squeeze them together any further, making them practically incompressible. But think about gases for a second. Because they are mostly just empty space with particles darting around, they have an indefinite shape, a low density, and crucially, they are highly compressible. You can easily squeeze all that empty space down. Moving right along to section 2, the invisible forces between us. We're zooming back into the atomic level here. Now, you might be wondering, why are some things tightly packed solids while others are free-flying gases? Well, it all comes down to intermolecular interactions. First up, we have London forces. Sometimes you'll hear these called dispersion forces. These are the absolute weakest of all the intermolecular forces, and they operate at extremely short distances. But here's what makes them so amazing. They are present universally. Every single atom and nonpolar molecule shares this fleeting, basic connection. It's essentially the bare minimum baseline of physical attraction in the universe. Here's how they work, and I want you to imagine this happening fast. Think of electrons buzzing evenly around a nucleus. But in a split second, purely by chance, the electrons swarm slightly more to one side. Boom, you instantly have an uneven distribution, creating what's called an instantaneous dipole. One side is briefly negative, the other positive. And this split-second shift immediately induces the exact same shift in a neighboring atom, setting off this chain reaction of brief, flickering attraction. It appears, it pulls them together for a microsecond, and then vanishes, only to reappear somewhere else. Now, if London forces are fleeting microsecond encounters, dipole-dipole forces are kind of more like dedicated relationships. These occur in polar molecules, which are molecules that are permanently lopsided in their charge. Because one end is always positive and the other is always negative, they constantly attract each other. It's a much stronger, far more stable interaction than a simple London force. Now, what's really interesting about this slide is how perfectly it proves the power of these invisible forces. We're looking at 2 substances here, propanone and N-butane. They have the exact same molar mass, both clocking in at 58 grams per mole. But just look at their boiling points. Propanone requires a massive 329.3 Kelvin to boil, while N-butane boils way lower at just 272.6 Kelvin. Why the big difference? It's because propanone is polar. It has those stronger dipole-dipole relationships locking its molecules together, which makes it much harder to tear them apart and turn it into a gas. And that brings us to the absolute king of these interactions, hydrogen bonding. It's a supercharged, exceptionally strong type of dipole-dipole force. And guess what? This finally resolves our hook from the very beginning. Hydrogen bonding is exactly why ice is lighter than liquid water. As water cools and freezes, these hydrogen bonds force the molecules into a highly specific, open hexagonal grid. It actually pushes the molecules slightly further apart than they are in a liquid state. More space simply means less density, and therefore ice floats. Oh, and fun fact, this incredible force is also exactly what holds the two strands of your DNA double helix together. Okay, let's jump to section 3, the laws governing gases. We're zooming back out to the macro level now. We've seen how strong forces make solids and liquids, but when those forces are essentially negligible, gas particles obey their own strict mathematical rules. Welcome to the alphabet soup of gas laws. Let's start with Boyle and Charles. Boyle's law tells us that if you keep temperature constant, volume and pressure have an inverse relationship. Basically, if you squeeze a gas to make its volume go down, the pressure shoots up. Charles' law, on the other hand, is a direct relationship. If you keep pressure constant and heat a gas up, so temperature goes up, the gas naturally expands, meaning volume goes up. And actually, Charles' law leads us to one of the most fascinating numbers in all of science, -273 degrees Celsius. Think about it. If volume shrinks as temperature drops, Charles' math suggests that if you cool a gas all the way down to -273 degrees Celsius, its volume mathematically reduces to absolute zero. At this hypothetical point, the gas would literally cease to exist. We call this absolute zero, or 0 Kelvin. Mind-blowing, right? So the crucial point is that all these variables are completely interlocked. Gay-Lussac's law shows us that if you lock the volume, say by putting the gas in a rigid steel tank and turn up the heat, the pressure goes up because the particles are hitting the walls faster and harder. Finally, we have Avogadro's law. He realized that if you keep temperature and pressure the exact same, adding more actual gas molecules, meaning the number of moles goes up, means the volume it takes up must also go up. So equal volumes of gases have the exact same number of molecules. Moving on to section 4, the ideal gas equation. This is the grand culmination of everything we've built up so far. We've looked at pressure, volume, temperature, and the number of moles. 4 totally separate variables studied by 4 different scientists over centuries. But what if we could bring them all together into one grand equation? Enter the ideal gas equation, PV equals nRT. Honestly, it's a masterpiece of scientific elegance. It beautifully combines pressure, volume, the number of moles, represented by N, and temperature, into one single master formula. If you know any 3 of these variables for an ideal gas, you can instantly calculate the 4th. It unifies the whole shebang. But wait a second, what exactly is that R doing right in the middle of our PV equals nRT equation? Well, that is the universal gas constant. Its value is 8.314 joules per Kelvin per mole. You can kind of think of R as the cosmic mathematical glue. It's the specific constant ratio that makes the proportional relationships discovered by Boyle, Charles, and Avogadro perfectly balance out into a workable, equal equation in the real world. All right, last but not least, section 5, mixtures and movement. Let's move to this and see how this builds when different gases actually meet in the real world. So what happens when different gases actually meet and mix in our everyday lives, completely outside of controlled laboratory containers? Well, they follow 2 more brilliant rules. Dalton's law tells us that gases in a mixture basically just ignore each other when it comes to pressure. The total pressure in a room is simply the sum of the nitrogen pressure plus the oxygen pressure plus the argon pressure. They just add up. And then Graham's law of diffusion explains their movement. Gases freely intermingle. It's exactly why if you open a bottle of perfume in one corner of a room, those molecules obey Graham's law, spreading out and colliding until you can smell that perfume everywhere. Which brings us to the very end of our journey today, and I want to leave you with this to ponder. As you take your next deep breath, just consider what's happening. Your diaphragm expands your lungs, increasing the volume, which instantly drops the pressure according to Boyle's law, pulling in a mixture of oxygen and nitrogen that adds up perfectly according to Dalton's law. How absolutely incredible is it that these invisible, micro-level